So we've made the introduction. Thank you, and thank you everyone for your patience. I just want to introduce our speaker today, Rick Howard. He is a specialist in battery technology, and I want to extend my thanks to Rick for sharing his knowledge and experience with us today. So, Rick, having said that, I let everybody know that if they wish to ask you a question, they should put it into the chat box, and then we'll read out those questions. I also let everyone know that today's session is going to be recorded. This webinar is presented by the Graphene Council, and the content is from Rick Howard. I want to thank you again, Rick, for that. And with that, it's all yours. Let's go ahead.
All right, thank you. Metal that is used in lithium-ion batteries. And one of the primary goals of cell manufacturers and people that are in materials research is to lower the amount of cobalt that are in today's cell. So if we take a quick look here, I'm not going to get into too much detail on this Roland Berger slide, but it gives you an idea of the relative cost. And if you can see my cursor, this is the cost per kilowatt hours. The LCO is lithium cobalt oxide on the far left, $73 per kilowatt hour. Now this is just for the cost of a cell. That's not for an entire battery, which is a collection of cells and battery management system circuitry, that sort of thing. So those of you that are a little more familiar with the industry might realize that over here, the fourth from the right, is lithium iron phosphate, or nanophosphate as it's sometimes called, and it has one of the lowest costs. But if you'll notice the light blue segment of this bar, that's the processing cost. So the material cost for this, the iron is very cheap, but you've got to do this in a specialized atmosphere in the furnace, and that's what raises up the production cost for this material. So I'll leave this slide, but obviously it's there for your reference. So if we look at where we're going with cathode materials, the ones that are starting to make some noise in the market, they're out of the lab, they're at least in pilot development, if not beyond. They're down to, at most, about 25% cobalt, whereas the lithium cobalt dioxide is 60% cobalt. If you look at some of the prices, right now cobalt's about $20 a pound, 35 euros per kilo. That's twice the cost of nickel and about 4 times the cost of manganese. The other thing is that the cobalt market, because it's a strategic metal, is very volatile. I've seen prices $60, $70 a pound. And of course, that's something that would drive automobile manufacturers absolutely crazy, because they fight and fight and fight over every penny to keep their costs down. So what's required as we move into greater consumer acceptance of EVs is cathodes that provide a greater energy and also power outputs. I mean, power is your ability to accelerate without using up all the charge in the battery. And of course, the ideal is lower weight and less cost. And if you want to carry that to a ridiculous extreme, it would weigh 0 and it wouldn't cost anything. Well, we're not going to get there. So EVs need the energy for the long drive. Hybrid vehicles need power for a boost. So if you're trying to pass that tractor trailer and there's another tractor trailer coming toward you, you want to be able to accelerate nicely. An iron phosphate cell really is for acceleration. It doesn't have enough energy to get you 200 miles or even 100 miles. So the combination of new cathode chemistries and nanotechnology, which I'll explain in a little bit, are really the future for cathode materials, and nanotechnology is going to make an impact also on the anode side. So just a quick view of the electrochemistry, or the chemistry, if you will, that's going on inside a cell. All right. On the left, This is a diagram of lithium cobalt dioxide, if you will. The yellow dots are lithium. They can be extracted when the cell is charged. They cross this gap, which contains the electrolyte, which is a salt solution, conducts ionic species, but not electricity. It's stored here on the right in graphite, and graphite is a layered material, and the lithium ions very nicely fit right into those layers. And the anode is used for lithium storage. Okay, there's very little chemistry that goes on there. Okay, and then when you discharge the cell, the directions are reversed. The lithium goes from the anode back to the cathode. Electrons are generated, and that powers whatever it is that you're trying to power. So cathodes is really what drives the cell and drives your unit. They supply the energy to your entire system. And the real chemistry here is the reduction and oxidation of the metals that are in the lithium metal oxides of the cathode material. And when you talk about the longevity of a given cell, in general, you're talking about the crystal lattice of the cathode material as a stable entity. It doesn't change from one crystal phase to another, because whenever you do that, you wind up with dislocations in the cathode. There'll be areas where the lithium can't get to it or it can't get out of it. And whenever that happens, you're going to lose some capacity, which is just another way of saying you're going to lose energy from the cell. Now, the conventional materials, so the ones that are in use today, even the best cases right now, just don't provide enough energy to get that 200-mile range for electric vehicles unless, one, you've got thousands of cells. Yes, we're talking about a Tesla, which in general would mean it's going to be too heavy and you've got less passenger space. Or you've over-engineered the car. Again, we're talking about a Tesla. Now you've got low weight and you've got some streamlining, but this is quite costly. All right, so let's look at the different capabilities of cathode materials. Currently, we can get about 1,000 milliwatt hours per gram or 1,600 milliwatt hours per cubic centimeter from our cathode materials. As I pointed out earlier, this is sufficient for cell modules that would fit into smaller commuter vehicles, or even larger modules that would go into local delivery vehicles like vans. You can increase the energy output of virtually all of these materials by charging to a higher voltage, but that reduces the safety factor. And automotive manufacturers are not going to go there under any circumstances. They're just scared to death of any liability issues, and they don't want any events to happen with their cells. Now, developing materials that are combinations of nickel, manganese, and cobalt are capable of greater than 1,000 milliwatt hours per gram. But there are some technical problems with the cell chemistry that needs to be overcome. And the other factor about these species is that their power numbers aren't very good. In other words, if you're using them and you want to accelerate, it doesn't work as well as it would, say, with the phosphate. Now, that's where we might get into nanomaterials. As the particles of these species get smaller and smaller, their ability to handle rapid discharge, i.e. power applications, becomes better and better. Well, obviously, not all materials are going to provide the same thing. I mean, you go into a store and you buy a lithium-ion battery, there might be half a dozen different chemistries sitting there on the shelf. So I've identified the common species that you will find. The cobalt dioxide, the lithium manganese oxide, the second one, it's also called spinel, the lithium iron phosphate, this nickel cobalt aluminum combination, and finally this low voltage NMC species, nickel manganese cobalt. And then you get a lot of variations. Some of these will show up with dopants. For example, you can no longer, with very few exceptions, purchase pure lithium cobalt dioxide. It will be doped with titanium and magnesium, for example. And then they're also coating some of these with ceramic-like species to protect the electrolyte against the attack from the high voltage system. Now, the lithium manganese oxide and lithium iron phosphates are relatively low energy compared to the rest, but they're high power. So they really are suited for hybrid electric vehicles. And the other thing I believe I mentioned earlier is that the iron phosphate is a low density material. You just simply cannot fit as much of that material into a cell of a given volume as you can others, which are 60% higher density. So now we look at the cobalt and nickel containing oxides. They're medium energy, or medium as compared to where we like to be, but they're relatively low power. So the highest capacity species that you get from my list, the NCA, nickel cobalt aluminum, and the NMC, nickel manganese cobalt, are roughly equivalent in what they can produce. So what can we do to make things better? Well, here are a couple materials that are already starting in the market. Relatively small applications right now. This nickel manganese is a spinel structure, and then this non-stoichiometric nickel manganese cobalt. And the commonality here is that these are high voltage materials. They're charged somewhere around 4.6, 4.7 volts as opposed to 4.2. The spinel, again, is relatively low capacity but very high power, whereas the NMC species here is just the opposite of that. Now the problem is that the high voltage will degrade the electrolyte and your cell life is much shorter than you would like. For example, the goal for automotive manufacturers is 1,000 charge and discharge cycles. You're very unlikely to get that with these species unless you can do something to protect the electrolyte solvents from attack by these species. And here what's happening is that these compounds are coated with ceramic-like materials, aluminum oxide, for example, or magnesium oxide, and many variations on that theme. The development in this area is almost frantic. There's some specialty applications that are using the manganese nickel spinel, but that is susceptible to capacity fade because some of the manganese can be leached out of the species, and then that gets over on the anode side and interferes with the performance of the cell. The NMC material gets a phase change as it's charged and discharged, and it starts to form a lower voltage spinel structure. You get a voltage phase. If you remember, energy is current times voltage. So as the voltage goes down, and it can be 10, 11% in the first 50 cycles, you're going to lose energy out of this system also. So let's talk about the structure for a second, and that's really a key to the performance of these cathode materials. So if we start in the center, we're looking at a spinel, and it has a cubic structure, which means that we're looking at one face of a spinel, but it doesn't matter. We can look at any face of the spinel; they all look the same. So when you're discharging the cell, as the lithium approaches this structure, it doesn't matter what direction it's coming in from, it always has access. And therefore, you get very rapid lithium diffusion. and good power. Now we move to the left, we look at these layered uh, lithium metal oxides where the metal is cobalt, nickel, or manganese or some combination. And now we've got the lithium is all in two dimensions. In other words, it's in a layer. And when you're discharging your cell, there's only two directions that the lithium can come in. Automatically, that's going to restrict some of the power capability. And then finally, on the right, we have a schematic of the crystal structure of the lithium iron phosphate. And these, again, the lithium are in yellow. These channels run only in one direction. Now, how do you get any power capability at all out of lithium iron phosphate? Well, one is that the particles are extremely thin. They're on the order of 30, 40, 50 nanometers. And these species are coated with a highly conductive layer of carbon. So if we go back to the layered lithium metal oxides, the lithium to metal ratio is highest for these species, and therefore potentially you have the greatest energy output. Now let's take a look at what we can expect in a year, 2 years, 3 or 4 years. All right. These high voltage nickel manganese cobalt compounds, 250 milliwatt hours per gram capacity, milliamp hours per gram capacity, excuse me, averaging about 4.2 volts. So if you just do the multiplication, you're at greater than 1,000 milliwatt hours per gram, which is at least 40% improvement over where we are today. As I mentioned earlier, the fatal flaw so far is voltage slippage. You revert to a spinel, you lose energy. However, when I say very recent paper, this is a Jeff Don paper, if you know the name. It is available online, but it has not been put in print yet, and says that a different preparation condition of these NMC compounds will stabilize the structure and prevent this reversion to the spinel lattice. And it's actually a fairly simple fix. Instead of annealing the material after it comes out of the furnace, you quench it, which means you drop the temperature very quickly, and then you lock in the desired crystal structure. So this reopens my optimism for an electric vehicle battery with the desired range, and a range that consumers would also like to see. All right, so that's pretty much it for the cathode side. That's where we are and hopefully where we're going. But you've got to consider the anode. The anode, as I said before, is where lithium is stored. And right now we're using graphite anodes, where the best one has about 340 milliamp hours per gram. And you say, well, okay, that's more than, maybe that's 3 times or 2.5 times the capacity of today's cathode material. And that's fine, but what you have to remember is that the density of graphite is much less. It's at best half that of the cathode material. So you simply can't fit as much graphite into a given cell as you would want. So for example, if you increase the capacity of the cathode material by 50%, to pick a number, then obviously you've got to put in 50% more graphite to accommodate all that lithium. But that 50% more graphite in a cell is going to crowd out the cathode material. So when you get done with running the models for this, you find out that this low density graphite is going to result in almost no gain in the energy of your cell. Now, if you do a rough estimate of how much you're going to have to improve your anode capacity, it needs to be about twice that of the cathode. So regardless of what you're putting in there for a cathode, your anode is going to have 500 maybe milliwatt hours milliamp hours per gram capacity. Samsung has done some more sophisticated calculations than my rule of thumb, and they believe that if you have a 250 milliamp hour per gram cathode, you need a 650 milliamp hour per gram anode to get you to that 200 miles or 325-kilometer range. Well, as I said near the start of the presentation, there's a lot of hype about silicon right now. The nice thing is that silicon can absorb more than 10 times as much lithium as graphite. However, silicon expands as it absorbs the graphite as much as 300%. And if you think about the design of, let's say, your laptop, the cell compartment in the laptop is designed to within a millimeter or two. And if the cell in there is going to expand considerably, you're going to start doing a lot of damage to your laptop. So that's simply not acceptable. You could even rupture the cell, which is really not acceptable. On a less alarming note, the repeated expansion and contraction of the silicon will fragment micrometer-sized particles. And that results in a loss of electrical contact between the particles. So you have areas that are now dead. They can't absorb lithium or get rid of the lithium. And the result is that the energy fades very quickly in these cells. Now, if you nanosize silicon, whiskers or fibers or nanoparticles, in the lab, they're getting really, really good results. And there are people that are working very hard to commercialize these systems. But the processing costs for this are quite high. And to my mind, it's not at all clear how manufacturers are going to justify 10x the cost for 50% greater performance. Now, there are a lot of other candidates for anode materials. Metal oxides, cermets, which are ceramic metals like nitrides, phosphides, carbides, things like that. And then there are metals that will alloy with lithium, like tin, for example, or more expensively, germanium. And all of these materials have quite high capacities that on the surface would satisfy our needs. But, and there's always a but, there are two enormous issues to overcome. The first cycle, you get an irreversible capacity loss, and subsequently you get very rapid capacity or energy fade. In the first cycle, when you charge the battery and lithium goes to the anode, you will get some phase changes. In some cases, they're trapping the lithium. The lithium can't get out, or there's been discontinuity in the crystal phases in the anode, and lithium can't get past it. And so you lose from the charge-discharge cycle as over half in some cases of the lithium that's available. So even though it looks like on paper you're getting very, very good results, when you start to go to the second and third cycles, there's not so much there. And then, again, we're not talking about plastics here. We're talking about ceramics. They don't expand and contract well. And so you get fragmentation and, again, lack of electrical contact and a rapid capacity drop. And this gives you an idea of what I'm talking about. So if you start with a film, as some companies do, and after you cycle it a number of times, you get this pretty ratty looking surface. And again, there's a loss of electrical contact. If you're starting with micron-sized particles and they start to break up, I don't like this particular cartoon because this should be very irregular. They don't break up into spheres. They break up into very irregular particles. Now, what's being promoted in the industry is these nanowires or nano whiskers. When they absorb lithium, they only expand along the radius. They don't expand along the length. So you space these nanowires such that even that they can expand without impinging upon their nearest neighbor, right? Very elegant concept. My concern, and it's not just for lithium here or for silicon here, but for other materials, my concern is that the processing to make this is expensive, and can it be scaled up to the point where you can make acres, thousands and thousands of square meters of this material that's going to be necessary to supply the industry? The jury's definitely out on that, but I'm kind of skeptical, as you can tell. So let's look at nanoparticles for a moment, nanosizing. I mean, in theory, it'll solve all the problems. Nanoparticles will allow very high rate. Lithium diffusion distances are very short. You're almost reduced to a two-dimensional rather than a three-dimensional particle. Your energy output is as good as it gets because you have very few crystal defects, so you're not going to trap lithium in there. So you're maximizing the utilization of the material. In practice, however, there are problems. The handling of nanoparticles is very difficult. Biparticles tend to recombine. Some of these are made as dispersions, but the solvent that's being used in the dispersion may not be compatible with the system that you use in a cell. Further, these are very high surface area materials, and controlling the viscosity of the slurries that you need to coat and make electrodes, that can make that whole system very, very difficult. Process costs go up. Nanoparticles are a possibility. I think they're going to be pretty expensive in the short run. However, can graphene help us out? I think it can. Of course, the definition of graphene is you've got a one atom thick layer of graphite. However, there are manufacturers that are jumping on the marketing aspects of this. As a purist, I don't care for their definition, but they're saying if you've got fewer than 10 layers, then it's still graphene by their definition. And I think that it reflects the processing inability to consistently produce a single layer sheets. Is there still an advantage? Yes, I'll talk about that in a minute. I mean, even if if you've got less than 10 layers, you're still better off than if you're using graphite. All right. Now, what makes graphene so good is that it has an extreme conductivity. It really will help lithium-ion performance. You get this incredibly fast lithium transport or diffusion. Your rate capability goes way up, which means that your power output is enhanced. And you get a synergistic effect with the surface species. Now, the surface species can't be too big. We'll talk about that in a minute. So they're going to be nano-sized themselves. Another positive for graphene is that it allows very rapid thermal conductivity. And heat is a real enemy of lithium-ion batteries. If any of the negative chemistry that's going on in there, like solvent degradation, accelerates as the temperature goes up. So if you're able to dissipate the heat that's evolved by the use of the cell, then you have a big plus. So a quick look at graphene. I'm sure you're quite familiar with this picture. A high resolution tunneling electron microscope with the holes here are about 2 angstroms. The roughness or the three-dimensionality that you see here approximates the electron clouds. And those electron clouds hold the decorations, the species that are on the surface of this graphene, they hold them in place. And you don't want them wandering around because then they can recombine, all right? And that electron cloud also produces the very high conductivities that I mentioned a moment ago. The other thing about graphene is that it's very flexible, and during the cells will expand and contract during normal use. Because the graphene is so flexible, it's going to be breakage resistant, and that will again go toward better consistency, quality control of your cells. So the whole end point of my talk, I've got about another 10 slides here, is decorated graphenes. There's probably hundreds of decorated graphenes that are looking at this issue of nanoparticles that are adhering to the graphene surface and used for some type of energy storage. It may be supercapacitors, but more often it's batteries. So you get the increased conductivities between these decorations. They are held in place by the electron cloud. Without that, these species will tend to attract to one another and they will agglomerate. Now, in the first step, that's okay, but then as they start sticking together, you get expansion and contraction, and you'll get cracks in the agglomerate. And that's the negative, because where you have those cracks, then you lose electrical and ionic conductivity. The absorption of these into these decorated species is better. Electrochemical performance improves. The small particle size of the decorations allows you to get as close to theoretical lithium uptake, so you're going to get greater energy possibility from your cell. The high conductivity, as I said earlier, gives you very rapid lithium diffusion, and you get greater power. So really, a decorated graphene is helping both aspects of a lithium-ion battery. You're going to get greater energy, and you're going to get greater power. Too much decoration doesn't work out so well, and I've seen 3 or 4 papers about this where the graphene surface is covered with more than a monolayer of some material, and that will develop cracks. And then we get back to the idea that, well, that's losing conductivity, especially lithium-ion diffusivity. And so you're starting to hurt the energy output of a given cell. You do get performances that are close to the theoretical with this. There is a synergism between nanoparticles, regardless of what they are, and the graphene. The graphene actually adds to the capability of the decorated species. So you start looking at some of the numbers, and what you find is that this combination or this composite with graphene, the performance data always exceeds that of the lithium storage species by itself. And that enhanced conductivity that is lent by the graphene is really the key to what's happening. You have particle accessibility, you have small size, there's no impedance to storing the lithium. So you're maximizing the capacity and you're maximizing the power. So this is what we might see. There's this particular cartoon shows different ways that species can be stored on the surface of graphene. In the upper left are the ones that we're most talking about here, in that we have separated nanoparticles. They don't have to be as nicely ordered as they see here, all right? But they're discrete units. Then in the upper right, we get something like a nanoribbon. So for example, if you're working with vanadium oxide, which is a possible anode material because it will accept lithium in storage, it tends to form as its own sheets or ribbons or whatever, all right? However, you're starting to crowd things together, and again, you can get breakage. You can get uh, well-ordered molecular species, as shown here. Again, they're rather large, or you can get agglomerates in the lower right, and we've already talked about the problems that you have with agglomerates. To give you an idea of, in my mind, an ideal species, here's a scanning electron microscope picture of silver on graphene, and you can see the little nanodots of silver. By my estimation, they're on the order of 2 or 3 nanometers each, well dispersed across the surface, and they're held in place. This is not an anode material per se, but it was a beautiful description of what I was trying to talk about. So if we look at a few companies that are working in this area, and this by no means is a complete list, but they're the ones that have marketed themselves. You'll read about them here and there. Silicon Graphene Composite by XG Sciences. They're actually selling these. They have different compositions depending on the silicon content, somewhere between 500 and 2,000 milliamp hours per gram capacity. The first cycle capacity loss is on the order of 10 to 15%, which needs a little bit of improvement, but it's actually fairly close to where you get with graphite. The best graphite first cycle capacity loss is on the order of 7%. Now, the problem here so far for electric vehicle batteries is that the current price of this material is still pretty close to $100 a kilo, whereas your best graphites are $10 to $15 per kilo. So that $100 a kilo, or roughly, is still way too high for a commodity material that's going to go into a consumer battery. Other companies working on these graphene silicon composites include Cal Battery and Vorbeck Materials, and they're touting some very high power ratings from their material. Then there's a company in Canada called Graphite, north of Montreal. They have a process to make graphene that's relatively mild as compared to some of these other companies which use high temperatures, very acidic environments. And Graphite is looking for partners to make derivative materials from their graphene. And if you follow Google alerts or something like that, you'll find new companies making graphene products for batteries popping up almost every day. There are hundreds upon hundreds of research groups and companies out there that are making graphene for a variety of uses. Here, again, this is a busy slide, but a bunch of examples more for reference, but I'll just run through them very quickly. Cobalt oxide, 2 to 3 nanometers, very, very small, on graphene, but stack graphene. So there's a few layers, it's not single. But here you're getting greater than 1,500 milliamp hour per gram capacity. It turns out that the cobalt preferentially attaches to the defect sites, which reduces the capacity a bit. But notice that the theoretical capacity for this cobalt oxide is about 900 milliamp hours per gram, and you're getting 60% more than that. Another application, oh, by the way, the cobalt's going to be fairly expensive. I'm not sure that that's ever going to be commercial, simply because of the price, not just of the graphene, but also of the metal involved. Molybdenum disulfide, you can make nanosheets fairly easy. You can mount them on graphene. You get more than 500 milliamp hours per gram with really good power applications and very, very good stability. So if you discharge your cell, now 2.5 C means you're discharging your cell in about 25 minutes or less. And you're getting a very stable system, so you're not losing nearly as much capacity as you would in other battery chemistries. If you look at the nanosheets by themselves, they deteriorate pretty quickly. And if you look at the polydisulfide powder, 3 or 4 cycles and it's done. Um, Tin, I mentioned earlier, is a metal that will alloy with lithium, and so it is an anode candidate. If you put it on a short stack, um, you you look at this, 4,000 cycles at 1C discharge. Now 1C is a 1 hour discharge. You figure your laptop cells are rated for C over 3 or C over 4. In other words, they last 3 or 4 hours. In 1C, that's pretty darn good for an electric vehicle. Electric vehicle is probably around half C, or a couple hours, maybe 3. Right? So very, very good capacity or energy retention here. Tin by itself goes nowhere. And then just a little bit different chemistry. Graphene can be doped with both nitrogen and boron. Not too difficult from what I read. And with these materials, you can have a standalone anode. In other words, you don't have to decorate it with something. The reversible capacities of these materials are greater than 1,000 milliamp hours per gram. And if you, excuse me, if you increase the rate to 120 C, now that's a 30-second discharge, you're still getting a substantial amount of capacity both from the nitrogen and the boron dope. And you get very, very little capacity fade, and you're not damaging the material, so you can completely recharge this. Now the doping results, and this goes to why it works so well, the surface morphology of this sheet, if you will, is no longer nice and flat, it's wrinkled. All right, so you've got quite a bunch of disorder there. That enhances your ability to wet this, so if you're going to make a slurry. It also enhances faster lithium diffusion, and the conductivity actually improves. Even though graphene by itself is very good, these doped graphenes are even better. Now, not to leave out the other electrode, graphene also assists cathodes, although there's much less work that's been done in this area. But cathode rate capability and cycle life are improved. Again, you've got to be mounting nanoparticles of this, and the cathode system is much more complex than the anode, which is why you don't see as much work in this area. Now, here's one example that I came up with to prove the point. So you take the lithium manganese oxide, you coat it with yttrium oxide, so it's a ceramic, basically, and then you mount those particles on the graphene. Well, the oxide layer prevents manganese from leaching, so your capacity loss, your capacity fade is minimal. This is actually wrapped in graphene, so it's an envelope, and it's accelerating the lithium diffusion. Now here at 30 C, 2-minute discharge, you're still retaining 90 milliamp hours per gram, or something over 300 milliwatt hours per gram energy output. And the capacity retention after 500 cycles, the 1C rate, that's pretty good, but the 55 degrees C temperature is extraordinary, that you can get almost 90% capacity retention after 500 cycles at this high rate, or high temperature. That would just destroy an unprotected lithium manganese oxide. So between the oxide coating and the graphene, you've really got a material extraordinarily good for power applications, but you're also getting more capacity than you would expect, so more energy. So getting close to the end here, will electric vehicles succeed? Well, the battery costs have got to come down. Predictions for the end of the decade, again, these are marketing predictions. They're saying cost reductions are going to be 60% from where they are today. The average automotive electric vehicle battery, lithium-ion battery, somewhere in the $6,000 to $10,000 range, depending on the size. That's got to come down, and it's got to produce more energy. Uh, as I said earlier, EVs today, uh, only consumers uh, without the fast charge stations um, can use them. It's only about 3% of the 12,000 public chargers that are out there. A level 3 recharger is a very rapid recharge, less than 5 minutes. Very few of them are available today. So if we look ahead a decade, what we would like to see for the proliferation of electric vehicles is lithium-ion batteries with 2.5 times today's energy, 2,000 plus cycle life, and improved power capability. And a lot of this is my opinion, but I believe that graphene is a critical technology for the success of electric vehicles. There's some very optimistic predictions of the consumer EV market, and they assume and depend upon scientific and engineering advancements. If we can't get to the stable high voltage cathode materials and the high capacity anodes, which I believe need to be these decorated graphenes, then we're not going to see real success in electric vehicles. You need some sort of a graphene assist. Otherwise, you're just not going to have enough lithium storage to match these next generation cathode materials. The fact that you can get rapid recharge, rapid discharge, facilitated by this combination of nanomaterials and graphene really speaks to an electric vehicle that not only has a long range that can get you where you want to get to, not just to your office that's 30, 35 miles away, but it can get you to the grandkid's house, which is 200 miles away. All right. What are the barriers? The processing of nanomaterials alone can be difficult to scale up. It's expensive. Those costs have got to come down. Graphene costs must come down. And on that note, we'll say Samsung has just announced what they claim is a very inexpensive process that will allow the formation of large area graphene. Now, how well that's going to apply in batteries, we need to see. But as I've said throughout my career, you do not want to bet against technology because if you do, sooner or later you're going to lose all your money. So thank you very much for your time and attention. Certainly there's plenty of time for questions. And if you would like to get in touch with me some other way, then there's my contact information. Thanks again.
Well, Rick, thank you. Really appreciate you sharing that information with everyone. Found it very fascinating and very encouraging. I think the path from where we're at today to commercialization looks pretty short compared to other historic materials development. If anyone has questions for Rick, please write them either in the question box or use the chat feature, and we can get those questions to him. I don't have any questions at this point so far, Rick, which is fine. So we'll just give a few minutes for that. What I'd like to do is just remind everyone that this session has been recorded, and we'll make that available to you after the recording is completed here. Also want to thank everyone for being a member of the Graphene Council. As I mentioned, we are the largest group worldwide now that's focused on graphene, 3,300 plus members and continuing to grow. So very excited about that. If you have any questions, you can also write me directly or get in touch with us if you'd like to find out more about what the Graphene Council is doing on standards development or events like the webinar that we had today. So, Rick, I don't see any questions coming in. So that means you did an excellent job of sharing that information and explaining this technology to everyone. So I really appreciate your time and effort. And we will not only make the recording available, but Rick, if you agree, we can make a PDF file of your slides available. You okay with that?
Oh, absolutely. No problem at all.
Okay. So we can share that with a wider audience that weren't able to join us today. So from my side, I want to say thank you to Rick again. Really appreciate the sharing of this information. And for everybody who participated, I want to thank you for being part of the Graphene Council. Tell your friends about us if they're not already a member, and encourage us to get into the largest community focused on the research, development, and application of graphene worldwide. Thank you for participating today.
Thank you, Terrence. Take care now.
Thank you.